Right, in this first problem, it says to calculate the percent of a reaction, 0.54 molar HCN, which is a weak acid. And so when I think of percent reaction, I'm immediately thinking of percent ionization, which should be your hydrogen concentration over your original acid concentration times 100. And so we have our original acid concentration right there. So what we need to do is find this at equilibrium. If you keep reading, it says in a solution that also has 1.05 molar KCN. And so this is a salt. So anytime I have a salt, I kind of want to think, what would that break down into? So KCN would break down into potassium and cyanide ions. And we know these when I do any reaction, but this could continue on. And immediately that looks like a base, and it's the conjugate of HCN. And so I want you to try and recognize this, because when you see a weak acid in its conjugate base, or a weak base in its conjugate acid, that means we have a buffer. And the reason recognizing that is important is because we can skip some ice tables to solving this. Like usually we would do an ice table to find this at equilibrium. And then for CN, we would have to plug this in initially. But what we can do is if we recognize this is a buffer, instead, we can go straight to this formula. A hydrogen concentration equals Ka times the molarity of your acid divided by the molarity of your base. And this lets us skip an ice table where we would have had to plug this in initially, and keep working it down until we found this. So let's do this instead to make it easy on ourselves. And this will give us the hydrogen concentration at equilibrium that we're missing. So we would say hydrogen equals, it has to be Ka. We have Ka, 6.2 times 10 to the negative 10th. The molarity of the acid was already given to us, 0.54 over the molarity of the base. I know that's the molarity of the salt, but salt's ionized 100%. So if this is 1.05, this is 1.05, this is 1.05. So we can plug that in for our base concentration down below. And we're gonna go ahead and get that number. All right, so we get this number for our hydrogen concentration. And so to finish our problem, our percent reaction would be our hydrogen concentration divided by our initial acid concentration times 100 to get our final answer. So we should get 5.9 times 10 to the negative 8th percent of it reacts, which is not a huge percentage, but we have a really weak. Okay, in this problem, we have a saturated solution, which means at equilibrium, and it's of copper sulfate. And the way we're going to make that is we're going to dissolve it in a lot of copper sulfate into 1 liter of water. But in that liter is already a salt, right? That alkali metal with sulfate. Once I put that copper sulfate on there, only 52 milligrams of it dissolves, and it says find KSP. So whenever it's asking for KSP, it's asking about copper sulfate. We're never going to find a K for a salt. Those ionize 100%. But we should consider the salt. So the salt breaks down into these ions. If we know the molarity of the salt, then we know it should be double for potassium and the same amount for sulfate. Now when we focus on copper 2 sulfate, it would break down into copper and sulfate. And this is what I would write out my equation for KSP to be. Remember, KSP shouldn't have a denominator because it always means a solid going into ions. And so I could plug in the molarity of copper here and the molarity of sulfate here and find KSP. I already know part of the sulfate, right? That's coming from the salt. I don't know copper. So I need to find this first in order to find KSP. So if I could just find the molarity of this, that's called molar solubility, that's X. These should be the same molarity at equilibrium because it's a 1:1:1 ratio. So I'm going to take my 52 milligrams, get it to grams, get it to moles, and divide by volume, and that'll be molarity. And that's what I'm going to plug in for these two. But for sulfate, I'm also going to add that additional sulfate that's already in the water. because it's there. So I took my 52 milligrams and I got it to grams. It was 0.052. I divided by molar mass to get moles. I got 0.000326 moles. Divide by a liter, and this is what I'm getting for molarity. So in my KSP formula, I would plug that in for copper, right? And then I would plug that in for sulfate plus the sulfate coming from the salt. If you forget to do this, you're gonna get an answer that's super, super close. But just in case your answer choices are all close, make sure you go back and you add that in. And so once we solve for this, that'll be our KSP, and it ends up being 2.22 times 10 to the negative fourth. No unit on KSP, and that makes sense. This thing doesn't have a lot of it dissolved in 1 liter. It should be mostly reactants at equilibrium. That's why it has a K anyway. All right, next we have pH of a buffer. I love these problems because I have that little formula for you when we recognize it's a buffer that we can skip the ice tables. And this one, we don't even have to recognize it. It's straight up telling us it's a buffer. So when I see buffer and it asks me for pH, I'm gonna think of this formula right here. Acid concentration over base concentration. And then I'm gonna solve for that. I'm gonna get hydrogen concentration. Then we'll end up taking the negative log of that. And then we'll be done. We'll have pH and we won't have to do any ice tables. So I'm gonna pause that, plug things in, solve for it, and I'll come right back and take the negative log with you. All right, so when I work this out, I'm getting this as our hydrogen concentration, which isn't a lot. If I take the negative log of that, I get 9.71. And that's okay, like don't freak out because we had Ka and everything. In our buffer, there's an acid and there's a base. And so we must have more base at this point. And so this would be our buffer, pH. Underneath that, we have an equilibrium constant, so capital K for HCN is this, all right? So we know Ka. This is an acid, so we can also say, okay, this is our Ka. Consider an equilibrium mixture where you have 0.2 HCN, so that just looks like we know the molarity of our acid to start, and then we're gonna add a salt. So if that salt has something in common, we might mess up equilibrium. Find delta G at 298 kelvins after NaCN is added. So it does look like it's gonna mess up equilibrium because I see cyanide here and here. And it's added so that the concentration is 0.35. And so that's describing this salt. Equilibrium has not been reestablished and assumed there's no change in volume. So when I see delta G and I know we haven't gone back to equilibrium, we must have Q. We need to think of negative RT, natural log of K, plus RT, natural log of Q, which we've done before. And so we know R, 8.314. We know our temperature, 298. We have our K, perfect. So really what we need to do is find Q. So let's think about this. We have HCN, our acid, and it was at equilibrium with this formula right here, right? And so what we can do is we can go through and we can figure out how we mess these up, specifically CN. So if I looked for Q when we're not at equilibrium, it would be hydrogen concentration over times cyanide concentration over our acid concentration, right? So what I'm gonna do is I'm gonna figure out what were these values at equilibrium so I can plug them in. And then since we added this salt, and salt's ionized completely, and this was 0.35, I'm gonna go in and I'm gonna add this molarity to my cyanide. But first I need to know what was it at equilibrium, and then I can add that, and that's how I'll find Q, because Q is when you're not at equilibrium and you have it messed up. So to start, we knew this was 0.2. These were zeros, and now it looks like a normal ice table, right? And so if I set this up equal to Ka, because that's at equilibrium, 6.2 times 10 to the negative 10th equals x squared over 0.2 minus x. I'm gonna go ahead and ignore this so I don't do the quadratic formula. And I'm gonna solve for x. And when I get x, that's gonna go here and here. I'm also going to add this to cyanide. And for this, I'm going to plug in 0.2 because that's what it was initially. And we ignore that x anyway for the quadratic formula. So let me find x real quick and we'll continue on. All right, so I'm finding this to be my x. So I'm going to plug that in for H. For Cn, I'm going to plug this in plus 0.35. And for HCN, I'm going to plug in 2. I'm going to find in Q and then start plugging things in up here. So this is what it would look like, whenever we solve for Q. I'm about to get that right here. And then I'm going to come over here and start putting my numbers in, or maybe down here, wherever I have room. So I got 1.95 times 10 to the negative 5th. So delta G is going to equal negative 8.314 times 298 times the natural log of K, which is 6.2 times 10 to the negative 10th, plus RT, 8.314 times 298 times the natural log of Q, which is 1.95 times 10 to the negative 5th. And so now I'm going to solve for delta G. And I just want to show you, Q is bigger than K, which means we need to shift to reactants. That makes sense because we have cyanide being added. So we need to shift to reactants. And so if we're shifting to reactants, this should end up being positive when we're done with it. So these are just good conceptual ways to ask yourself, like, does this make sense? So let's get our answer, and I'll write it down here because I'm running into things. And so this is what we're getting for delta G. And conceptually that feels right, positive delta G. Let's go back to reactants. Okay, in this problem we have iron 2 hydroxide, slightly soluble. There's its KSP, so right away I know there should be a solid on the reactant side, and then it's going to break down into their ions, iron and 2 hydroxides. And so KSP would equal this times this squared. What is the pOH of the solution made from 0.3 iron hydroxide? So if I set up an ice table, we want to find pH and pOH at equilibrium. So I'm going to assume that 0.3 moles over 1 liter is the starting molarity. But then look, we're adding it to something already in there. And so this is a salt. It has that nitrate. And so this salt would completely ionize into iron and 2 nitrates. And so if we know this is 0.045, we know this is 0.045, and this would be double that because we make 2 nitrates. Well, what do they have in common? Iron. So I am starting off with 0.045 here initially. This would still be 0, so we're still going to shift to the product side. But we do need to have that initial amount in there from the salts minus that. Oh no, I don't even know why I put that in there. That's a solid. So now I would say, okay, KSP equals 4.87 times 10 to the negative 17th, which should equal 2x squared times 0.045 plus x, right? And so this kind of looks like it's leading up to a quadratic formula. Because this KSP is so small, we could get rid of this one to avoid that. Just because we don't want to get rid of both of them, right? That's the whole point. We got to find x to figure out what hydroxide is. But we could get rid of this one to avoid the quadratic formula. If you don't, you'll be fine. Our x's will be super similar. So let's go ahead and find x. Right here, this is what we're getting for x. And so we are going to plug that back in right here because we want hydroxide concentration. pOH, which we're looking for, is the negative log of hydroxide. So we need to do the negative log of 2 times x. So don't forget that 2. And once we do that, we're done. If it had asked for pH, that's when we would subtract from 14. But we have a base, so this will give us pH. All right, and when I solve for this, I'm getting 7.48 as my pOH.